Okay, we're going to continue on doing more trig substitution. I'm going to try to do two of them in the same video because the first one is a little straightforward and short. The other one will be longer and more complicated. So again, I wrote on the side there which trig function you want to substitute to help you get rid of the radical depending on the form that you have. So, the good thing is, one, I'll give you these. So you don't have to worry about memorizing them. But, if you ever see the plus, right? Tangent is the only one that has the plus. So, it's either x squared minus something or something minus x squared. And in that case, you would pick sine or secant. So here I have 1 minus x squared, which is awesome because if it had been 4 minus x squared, I'd have to pick 2 sine theta, right? If this was 9, I'd have to pick 3. So it's a 1, yay. So I'm going to pick 1 sine theta. But that makes dx ridiculously easy because the derivative of sine is just cosine. Make sure you put your d theta there. Now I'm going to go make my substitution. I'm going to put the dx on the top. And then I'm going to put sine right there. And, I'm just going to write sine squared because it's easier in this case. Right? You're doing sine theta and you're squaring it. So normally I would do this radical work on the side, but I don't need to. I don't have a number that I'm factoring out. It's really simple. I'm just going to put cosine squared right there. So this is one of the few times I would not do the radical on the side. I know that 1 minus sine squared is cosine squared. I also know that the square root of cosine squared, I guess I'll come back over here, is cosine, right? You're taking the square root of the square. So you just get cosine. And now look what happens. Cha, cross them out. It's very important. You have 1 d theta. Once you make this, this problem is almost trivial. Once you put everything in, it just crosses all out. But you still have a 1. I don't like the way my d looks. It's got to look nice. Okay. Now, if this had just been x, if this was the integral of 1 dx, right? Then it would just be x, right? The derivative of x is 1. Here, though, you're integrating with respect to theta, right? We don't have x anymore. So this is just theta plus c, right? If you take the derivative of theta, you get 1, right? It's just like an x. Treat it like an x. It's still a variable. Now, the problem is I don't, I have nothing to replace here. It has to look like this, kind of, sort of. So the only thing you could do is go back to where you started and solve this for theta. And as I said in class, you can't get the angle alone unless you do our good buddy inverse. So if you take the inverse of both sides, right? You have sine and then you do its inverse. Remember, the inverse of sine is not cosecant, it's not cosine. Right? Cosecant is the reciprocal of sine, right? They're partners. They're the opposites, right? The ratios of the sides of right triangles, right? The sine is the opposite and the hypotenuse. So his partner is hypotenuse over opposite. That has nothing to do with an inverse, right? So the inverse just crosses out the original guy and you get theta, right? You do the sine inverse of sine, they wipe out. So that's it. Where theta is, you would put inverse sine of x. Now, I know the books, and, I'm sure plenty of the solvers out there will write arc sine. It's not wrong. That's what the inverse sine is called. They came up with these cute little fancy names. They call it arc sine, arc cosine. But for us, right, that's not a power, right? It means inverse. Back in the day in pre-calculus, you wrote this down. When you did the inverse of a function, you wrote f minus 1. So here, the only way to get the angle theta, you don't need a right triangle in this case. You don't have to draw the right triangle. You just replace theta with the inverse. And in this case, since I use sine, had I used tangent here, it would have been inverse tangent. Okay, so it's always the inverse of whatever function. I'm going to try to do the harder one. Okay, I jumped over to 5. Maybe at some point I might go do 4, but 5's a lot more complicated and interesting. So I'm going to do this one. So if we use our guide, right, the previous one I just did was using sine. There's no plus, so it won't be tangent. So this time I'm going to pick secant. Now, again, it is annoying that you have a number here that isn't a 1. When this is a 1, it's great, because then you just don't have to worry about putting something in front. You just take the square root of whatever that number is, which is 5, right? Square root of 25. And it's going to be secant theta. So now I'm going to immediately take the derivative of that. The derivative of secant is secant tangent, so I put that there. Okay, so now I'm prepared to start plugging everything in. This time I am going to do work on the side here. So now you have to be very careful. Remember, this dx, even though it's written on the side, this dx is really up there on the top of this fraction. Like when you make the substitution, you have to make sure you don't take the dx and put it down here, because it's going to screw you up when you start canceling things out and simplifying it. So where the x is, I'm going to put 5 secant. This is why this time I will do this on the side. Where the x is, I'm going to put 5 secant. And then where the dx is, on the top of this, I'm going to put 5 secant theta tan theta. Now, yes, I could cross these out right now, but I'm not going to do that yet, okay? Oh, I forgot my d theta. It doesn't look right without it. Even I forget it, but it needs to be there, right? Remember, this is a derivative. You're finding an antiderivative. So now, again, I'm going to do my work on the side. I'm going to square that, right? So it's 25 secant squared. You always want to do this on the side, unless, you're really sadistic and you want to write this thing 80 times. So then I'm going to factor out the 25 from here and here. When I remove this 25, I get secant squared. When I remove that 25, I get a 1. There's a negative between them. Now I use the trig identity. Secant squared minus 1 is tan squared. Again, remember it's theta. Square root of 25 is 5. Square root of tan squared is tan theta. All right, so I did all my side work, which allowed me to come back up here and put that over there. That's exactly what I'm going to do. So now I'm going to put everything on the top that goes there. So I have 5 tan theta. I already had that there, the secant theta tan theta. That was my dx, right? I put that as my dx. That goes on the top. And then on the bottom, all I had was just 5 secant theta. Now I am going to cross them out. Those go away. Those go away. So what I'm left with is a 5, and then tan and tan. So I have integral 5. Tan and tan make tan squared. Now we're going to finish this in a minute, right? So that's my initial move. Pick my trig identity. Make my trig substitution. Simplify my radical on the side. Plug it back in. Simplify as much as I can. Then I get here. Now I'm going to be ready to integrate this. So I'm going to erase everything so I have more room, because these take up a lot of space. Okay, so poof, like magic, everything else disappeared. So then I got to this stage. Now this is where you have to be very careful, because this integral can be really tricky. There isn't a way to do that. If you had, this is why we did trig integrals before we did this. If you had something like this, that would be the u, that would be the du, and then you would just get 1/3 tangent third. But you don't have a secant squared to be the du, so you can't do that one. So you got to use a little cleverness and trickery here. I'm going to take the 5, and I'm going to put it in the front. Just it's kind of annoying if it's there, and I'm going to do a move that helps me simplify this. I'm going to replace this with the trig identity, right? So this is secant squared minus 1. Right? That's my big move. I split it up. Now, I'm going to integrate this, and I'm going to integrate this. Maybe I should have left the 5 there, but it doesn't really matter. I have the 5. I'm going to find the antiderivative, right? By splitting this up, because you can't do the integral of tan squared. This is no one's derivative, but secant squared is. His derivative, right? I mean, the derivative of tan is secant squared, right? So derivative of tan, secant squared. Now, you have a 1 there. And again, remember, this is 1 d theta. D theta, not dx. So when you integrate the 1, I got to put my parentheses here. There's 5 hits both. That's going to be minus theta. And then the plus c. So technically, this 5 is supposed to go here and here. I'm going to do this at the very end, and you'll see what will happen. It may not even be necessary for me. This time, I have no choice. If I want to make this is my answer. I mean, I'm done. But I have to make it look like what I started with, which means I have to put the x's back there. So I'm going to draw my triangle over here. just for convenience. I mean, if I make it all the way over there, it's too far from me. So I put my theta here. Now remember, I started this question off with this. I had x equals 5 secant theta. Now, if I divide both sides by 5, I get, right, that secant theta is x over 5. Now, what I keep saying again and again and again, right? You memorize back in the day of trig, this SOHCAHTOA. And I would say, smelly old hobo, children are happy, tangerines or apples. You don't know them, right? Sine, cosine, tangent. You don't know them for secant, cosecant, and cotangent. So what you do is you find the partner, right? Secant's partner is cosine. And I know that the cosine goes with the adjacent side and the hypotenuse. That means that this guy is the opposite of that. But I don't want to have to do that. I don't want to play this game of switching things around. I want to make it really easy. So I'm going to figure out what cosine is. And I need it anyway. So cosine is going to be 5. Jesus, 5 over x. So worst 5 ever. So I use the secant to figure out which trig guy. So now, right, remember, this is opposite, this is adjacent, and this is hypotenuse. I mean, you know this already. So the cosine goes with adjacent side, which I'm going to put a 5 there, and the hypotenuse is x. And then remember what I said in class. You can do this like a dummy, or you can do this very intelligently. The side that is missing here is always the radical that was in the original equation. And as I said, you are more than welcome to use the Pythagorean theorem to see that it works, and it absolutely does work. So now I have the triangle. I also have this, which is awesome because I need theta. I mean, I have to put something here for theta. Okay, so that's why you want it to be in terms of cosine or sine or tangent, because I'm going to use those inverses. So I need to read tangent, right? So I still have my 5 here. I need to read tangent off of my triangle. Tangent, tangerines or apples, TOA. Tangent goes with the opposite side and the adjacent side. So tangent goes opposite over adjacent, which conveniently is 5. Whoops. Yeah, that's right. Opposite adjacent. So see what's going to happen. Now I do have to put this 5 over here. So I'm going to do it now. And I'm going to erase that in 1 second. Right. At this point, I'm going to distribute my 5. Remember, this 5 was attached to this. So when I replaced it, that 5 is supposed to be here and here. So, I mean, maybe you could have left it here, but you would have to distribute it out to there also. So it just doesn't matter. Now, to get theta, remember what I said. I'm looking for the angle this time. So I want cosine to be gone. So what I have to do is I have to do the inverse cosine to cross out the cosine. You don't just divide both sides by cosine, right? I need theta alone. So that means that theta, right, you're going to do the inverse cosine of both sides to kill the cosine part and leave you the angle all alone. So that's what you get. So I'm going to put this over there. So I have to rewrite a little bit. So it's 5 times inverse cosine of 5 over x. I mean, this is the only way you can get the angle. You need a trig equation that has theta in it to solve for theta by using the inverse. The inverse crosses out the original trig function. So that's my theta. I had to put my 5 there. Now I can just cross these 5s out. They don't need to be there. 5 divided by 5 is 1. So, yay, goodbye. So, made it a little easier for me. So, this insanity, if you were to take the derivative of it, would give you that. All right, so this is the final answer. This is the whole thing. So this one's a lot more advanced. There's a lot more stuff going on in this problem. In particular here at the end, you have to deal with the inverse. Again, this one I had to draw the triangle. The previous example I just worked number 3, I didn't have to draw the triangle. I just needed to do the inverse. But they do show up where you're being asked to replace the angle with something. So you have no choice but to use. But notice, the inverse uses the x's, right? I mean, you have to replace theta with something that has x in it. That's exactly what I did, but I had to use my original trig equation. So that's the number 5. I don't know if I'm going to do any more. These take a long time.